Okay, great. Hello guys, welcome to the class. So today we will do an interesting lecture about a very young field of graph representation learning. And it is all about how do we learn automatically representations of nodes so that we can then use those representations for various kinds of tasks, okay? And this is kind of very much motivated by the recent kind of developments in deep learning, and I will connect to that area as well, and you will see how this is kind of different, harder, and in many senses much more interesting. Okay, so what do we want to do? If you think about doing some kind of predictive task over a network, one example would be what is called node classification, where you have a graph. You have a graph semi-labeled. Some of the nodes are red, some are green. And the question is, what are the colors of, how should we assign colors of the gray nodes, right? So given this graph, I want to go and infer the colors of the missing colors of the nodes. This is what is called node classification, because I'm classifying each of the nodes, in this case, into two classes, green or red. Okay, that's one first example of the prediction task. A second example of prediction task is what we introduced in the last lecture when, with Baharan, when she was talking about link prediction, where basically the idea is I give you a network where most of the links are observed, but some are missing. Can you predict which means are missing in this network? And whenever we are trying to do these types of tasks, there's always kind of this problem that we need to do feature engineering. We need to take the network and somehow represent the nodes in a network with a set of features. And we can do this feature engineering by, for example, we talked about motifs, we talked about graphlets. These were all examples about how could you describe the node and the network neighborhood around the node with a set of features, right? So basically, we always have this idea that we need to take our raw network, our raw data, we need to create a set of structured data where we describe every node with a set of features so that we can then apply some learning algorithm and we can build some model that can do some prediction for us, some task, right? And what is kind of the most cumbersome part is this part where we say, how do we get from raw network data to this kind of feature description for every node, right? How do we do this feature engineering? Should we use motifs? Should we use graphlets? Should we use something else, right? And once we have these features, we can then apply them to some downstream task of clustering, analysis, outlier detection, link prediction, node classification, whatever you like. And what we'd like to go away is we'd like to skip this step of feature engineering, and we'd somehow like to automatically learn those features. And the way kind of we want to do this or think about this is that we want to basically go and do this kind of task-independent feature engineering in networks. And what we will try to do is we'll try to take a network and map every node in the network into some vector of numbers. Okay, and we will call this vector of numbers, we'll call it an embedding, we'll call it feature representation, this will be some kind of latent vector describing a node in the graph. And our goal will be to figure out what should be the coordinates of every node so that somehow something about this network is preserved. And when we say graph representation learning or graph embeddings, the idea is that I want to take every node and embed it in some d-dimensional space, where d is some parameter. Think of it an order of 100, an order of 1,000. Okay, that's what we are trying to do. So what do we want to do? We want to map each node of the network into a low-dimensional space. And this is very useful because if we can map nodes into low-dimensional space, then we know how to reason about data points. We can measure their distances. We can think about how they fill this embedding space, do any clusters emerge in there, and so on, right? And our main goal here is that the similarity in the embedding space should somehow reflect the similarity in the network, whatever that will mean, right? And this means that this will allow us to kind of encode network information and generate the representation for an individual node, right? So the idea will be that somehow we take our network, we create the adjacency matrix. Out of this, we can come up with an embedding for every node. And once we have every node described by the embedding, by the set of coordinates, we can do anomaly detection, we can do clustering, we can do link prediction, node classification, whatever we would like to do at the end. Okay? To give you a concrete example, here is a demonstration how this would look like if I take a network, in this case the Zachary Karate Club network, which we talked about before, as an input, and I want to embed the nodes in two-dimensional space, right? So in this case, d equals 2. So here is now the embedding of the nodes of this network in two-dimensional space. So every node has 2 coordinates, and I'm plotting the locations of the nodes after this embedding, right? And what you see is, for example, that nodes that are somehow in the similar part of the network, they also get embedded close together, right? So these guys here get embedded up there, the red nodes here get embedded there, and then, the violet ones are here, and then these, the green ones are somewhere here. These are 26 and 25. These are these 2 nodes, for example. Right, so you see kind of how, we took this network and now we were able to embed these nodes into this two-dimensional space, and somehow spatial positions of the nodes correspond to their their network positions and their network relationships. Okay, so this is kind of what this allows us to do. Of course, we won't be embedding in 2 dimensions, but we'll be embedding in hundreds or thousands of dimensions. Okay, now what I want to do next is kind of explain how this relates to this notion of embedding and feature learning that is coming out from deep learning, deep neural networks. And here is kind of why this is an interesting problem and very different than what we can do in computer vision or speech or text, right? So the modern deep learning toolbox is kind of designed for simple data types. It's designed for simple sequences or grids, right? What do I mean? You can take an image, represent it as a matrix, as a grid graph, and then you can kind of pass through this image through a super deep neural network to get some output you desire, right? And if you think of text you can represent as a chain graph, right? Text is a sequence, right? So you can now start reasoning about text at this level of a sequence. And again, in some sense, you have fixed size input because the window through which you are kind of going through the sequence is limited. And with images, you always resize all the images to have the same size. So again, the input is very simple. It's just a fixed size matrix, right? So it's a grid graph if you want to think of it that way, right? The problem becomes that real graphs are much more complex. They are not these nice kind of fixed size grids that you are inputting, right? So graphs have much kind of more complex topological structure, and they don't have this kind of spatial or grid type locality, because what do you do in computer vision? If you think of this as a vision, you have this kind of filter that you are sliding through across the image, right? And it's not clear how would you design these types of sliding filters over graphs, because graphs are kind of much more complex objects. The other thing that is important, for example, to distinguish between graphs and, let's say, images is that in graphs, there is no fixed node ordering, right? I can have adjacency matrix, I permute its rows and columns, that's still the same adjacency matrix, even though the matrix will, or the same graph, even though the matrix will look totally different, right? In the image, if I permute rows and columns, if I scramble them, that's not the same image anymore. It's a very different image. It's not a cat anymore, it's something else, right? In graphs, I can renumber the nodes, and the matrix will look very different, but topologically it's still the same graph. And the other thing that's interesting is that these graphs can be dynamic, can have features or values on nodes, on edges, and things become very interesting. Okay, so really, these types of graph and the representation learning on graphs is very challenging, in some sense more challenging than representation learning for text or images, because those are much simpler input data types. Okay, so now let me tell you how we are going to reason about embedding of graphs, right? So we will be given a graph which will have a set of vertices, a set of nodes, let's call it V, and we'll have A, the adjacency matrix. And for now, let's assume the adjacency matrix is binary, and we can even assume that it's symmetric, meaning the graph is undirected, right? And for now, let's assume no node features, no extra information on the nodes, anything like that. We are just given the wiring diagram. Okay, so a graph. And what we would like to do is, our goal is to somehow to take the nodes of the graph and embed these nodes in our embedding space, where every node has coordinates. We will call the embedding of the node z, and we want to, in some sense, learn this function we will call the encoder function that takes the node and encodes its coordinates. It determines its coordinates. And our goal will be that we take nodes from the network, and their relationship in the network is somehow encoded in their spatial position in the embedding space. Okay, that will be our goal. So if I now take this same picture and try to make things a bit more precise, I can say that the similarity of a pair of nodes u and v in the original network should be similar to the similarity of the coordinates in their embedding space. So then the question is, how do I measure similarity? One way to measure similarity would be to measure the Euclidean distance between the 2 points. What we will be doing, and what people like to do a lot, especially in high dimensions, is to use what is called cosine similarity. And cosine similarity, if all the coordinates are non-negative, is basically the dot product. Right? So the dot product between two vectors equals the cosine of the angle between the two vectors. Right? If the two vectors are orthogonal, then the similarity is 0, and they basically, if they overlap one on top of the other, then it's basically the length of the vector. Right? So this is the special case of cosine similarity, which is just the dot product between the coordinates of u and the coordinates of v. Right? So our goal is to say, I want to find the embedding so that the similarity in the embedding space relates or is similar to the similarity in the original network. And what is our task? Our task is to define what does this similarity mean, and how do we then determine the coordinates that optimize this network similarity. Right? So our goal will be to define this notion of network similarity and then optimize the coordinates so that network similarity is preserved. Okay? So here are kind of 3 steps to the algorithm. Right? So the first, we need to define an encoder, which is basically a mapping from nodes to embeddings. Then we need to define a node similarity function that will say how similar or how related are 2 nodes in the network. And then we need to optimize the parameters of the encoder so that the similarity in the network is as close as possible to the similarity of the embedding. Okay? Now, here is how we are going to think about this, right? So here I said optimize the parameters of the encoder. This may seem as if that encoder is this magic function that takes the node and produces the coordinates. And for us, we will consider very simple case of encoders. So let me tell you how our encoder will look like. Our encoders will be very simple, and all they will do is they will just memorize the coordinates of every node. Right? So basically, our encoder will simply memorize the coordinates. Right? So that the number of parameters of our encoder is the number of nodes times the embedding dimensionality. Okay, so we will just kind of directly go and learn coordinates of each node independently. Right? So this means that our encoder function is just a table lookup. Okay? I'll have a picture very soon about that. Okay? So now that I told you how do I encode a node by basically just directly estimating its coordinates, now the question is how do I think about the similarity function in the network? And the similarity function will specify the relationship between a pair of nodes in the original network, right? So in some sense, I want to say how similar are u and v in the original network, and that similarity should be encoded by the similarity of the coordinates of the 2 nodes in the embedding space, right? So I want similarity to be hopefully equal to the dot product between the positions of the 2 nodes, okay? So what we will do is the simplest thing, where we basically say that encoder is just an embedding lookup, which basically means that we will say the encoding of a particular node v is simply this encoding matrix times the one hot encoding of the node of the particular node, right? So this is really what we are trying to estimate. We are trying to estimate the coordinates for every node. This is what we will try to learn, And the vector v here is simply an indicator vector that has all zeros except 1, 1, which indicates what node is that. And to give you a picture, because that was kind of complicated, all I care about is to estimate this matrix where I have one column per node. The number of rows equals to d, the number of dimensions. Number of columns equals n, number of nodes. And each column contains the embedding for one node. Okay? And now my encoder, if I say give me encoding, give me the coordinates for node 5, the encoder goes into the 5th column and says this is the encoding. And if I say give me the coordinates for node 10, we go to the 10th column here and output that. Okay, so the number of parameters that we are trying to estimate is this matrix, is the coordinates of every node in the network. Yes? What determines the number of dimensions? This is a user-specified parameter. Okay, so user specifies that. The number of columns, the number of nodes is specified by the network. Sorry? It's a hyperparameter, right? The user decides what is the dimensionality they want to embed into. Great question. Thank you for asking. Okay? So, so we are kind of working now towards, basically our idea is that each node is assigned a unique embedding vector. And now we need to figure out how are we going to define the similarity. And today we will talk about two methods. One method is called deep walk, and the other method is called node-to-vec. So we'll first discuss the deep walk method and then generalize it to the node-to-vec method. And then at the end of the lecture, I will talk about not how to embed individual nodes, but how to embed entire graphs as well. Okay? So that's kind of the plan for the lecture. So now the key choice for us is how do you define node similarity, right? It's clear how we want to do the embedding and how we want to do the similarity in the embedding space, but the question is how do we define the network similarity? And there's many different ways to do that, right? So for example, early on people said, oh, two nodes are similar if they are connected, and if they are not connected, they are dissimilar. That's one option, right? Another option would be to say the similarity between nodes is the number of shared neighbors that they have, right? Or maybe that they have similar structural roles and so on and so forth. What has emerged as the best way to define similarity is to use random walks, okay? So we will use the technology of random walks that you are all very well familiar with by now, and we will talk about how can you use random walks to generate node embeddings, okay? Here are the links to the papers we will cover. One is from 2014, the other one is from 2016. So this is very recent work, okay? So how will this work? Here is our similarity and the embedding space between node U and node V. And we want to encode the coordinates such that the similarity and the embedding space equals to or approximates the probability that nodes U and V co-occur on a random walk over the network, okay? That is basically the idea. So to unpack a bit more, right? So what we will do is we will take some node U and we will simulate random walks starting at node U. And then we will ask how often or how does, if we start at node U, how often do we visit node V, okay? And then we will say, the probability that we visit node V if we start at node U, is some value, and I want this probability to be encoded by the spatial positions of node U and V, right? And I want that probability to be encoded by the angle between the two vectors, because this is kind of cosine similarity. So the smaller the angle, the bigger the cosine of the angle, the bigger the probability, right? And here, notice I'm like intentionally sloppy, so I just say it has to be proportional to, right? So basically my goal will be, once I know how likely are U and V to occur in random walks together, I will say we want to figure out the coordinates of the nodes such that this probability of co-occurring in the random walk is encoded in the similarity or the distance metric between the two vectors, which in our case is the cosine similarity or the dot product. Yes?
You say that this is the best way to do it, do you just mean it's worked really well?
Exactly. When I say best is state-of-the-art results on empirical data sets have been achieved using these methods. Yes. All right. And there are other computational benefits. So why do you want to do this, right? Exactly your questions. The first thing is that now you have this flexible stochastic definition of node similarity that kind of both incorporates local but also kind of higher order neighborhood information, right? It incorporates a lot of the network through this random walk mechanism. And the second thing is you don't need to specify similarities between all pairs of nodes while training. You only need to consider pairs that co-occur on random walks. So in some sense, you can simulate these random walks, get your training data, and then estimate the coordinates. Yes?
So this forces that similar nodes be relatively close together on the graph, right? Otherwise, the random walk isn't likely to reach from one node to the other. So how do you deal with nodes that have basically like a high topological similarity but are very far apart on the graph?
Great question. So the question is, do nodes that are very close together in the graph, are they always embedded close together? And could you have nodes that are in different parts of the graph maybe be embedded close together because they have similar structural roles? Wait with me for maybe like 17 slides and we'll address exactly that question. Okay, great. There was a question here? No question anymore? Okay. Don't be shy. Okay, so we continue. We will address your question. Okay, so these are some of the reasons why these are good ideas. Okay, so what's the intuition? The intuition is we want to find embedding of nodes in d dimensions so that we want to preserve similarity. And the idea is that we want to learn node embeddings such that nodes that are nearby in the network are also nearby in the embedding space. So now the question is, given a node U, how do we define what is close to node U? And the idea is that we will define this set N of N sub R of U to be the neighborhood of node U defined by some strategy R, right? So I will have some network exploration strategy. I will start at node U and I will ask what is close to U. And whatever is close to U, I will put in this set N, okay? And usually, I will have another hyperparameter that will tell me how big of this set I want to create. Let's say I want a set of 10 nodes. So I will say, what is the network neighborhood of node U of size 10? And I want to go and somehow identify this network neighborhood. So here is how you can do that. The idea is that we want to run fixed length short random walks, right? And then just record what are the nodes that the random walk visits. Okay, so basically I say, imagine I pick my hyperparameter value to be 7. So I will start at node U and I will simulate a random walk of length 7 and ask what are the node IDs I visited. And I will put this into the set N sub R of U. And I can go and create multiple instances of this set N because I can simulate multiple random walks all starting at node U. Imagine I sample, I don't know, 200 walks per node, so I will create 200 of these sets, okay? So now this means that I have defined this notion of a neighborhood. For node U, I have a set of neighbors, and these neighbors are determined by this random walk, walking for a fixed number of steps, where the number of steps is some hyperparameter, think of 5, 7, 10, something like that, okay? Now that I have these neighborhood sets, I want to define an optimization problem that I will use to figure out what should the coordinates be. So I will do the following. I will say, let me optimize the coordinates of the nodes, the parameter z, such that given node u, I can predict who its neighbors are, okay? So basically, I want to say I'm at node U and I want to predict who my neighbors are based on their coordinates and based on my coordinates. So here is the optimization problem, right? I'm saying I will want to maximize this function L that goes over all the starting nodes U. It goes then over all the neighbors of that U. And that says, oh, I want to maximize, here I have the log probability that says how likely, given that I started at U, how likely am I to start to visit node V? Okay, here I already have coordinates of U, and I will also use the coordinates of V to estimate this probability. So the question is now, how do I encode this probability? Yes?
Why do you take the negative log?
Oh, just, it doesn't really matter. I can call it a maximization or a minimization problem.
Like, why do you have the log there at all?
Why do I have a log?
Yeah.
Because it's a product of probabilities.
Oh, okay.
Right? It's a product of probabilities, but if I take the logs, then the product becomes the sum. And as I'm sure they have taught you in machine learning courses, you should never work with raw probabilities because multiplying them kind of screws you totally numerically. So you want to work with logs, and then the world is nice to you. Yes?
Is the multi-set the result of all the random walks, or just one random walk?
Yes. To be even more precise, what I would want to do here is I would want to have another sum that would index these sets as a number of random walks that I started over the node. So there should be multiple instances of the same set of the random walk starting at node U. Okay, so this is not a union of all the random walks, but for each random walk starting at U, I have a separate set. So in some sense, I'm missing another I here. That would be a sum over I random walks that I started at U, and each one gives me a different set.
You just append the list of all the neighbors of all the walks.
You can think of it that way as well. All right, great question. Super. So now I need to go and keep unpacking what this really means. Okay? So how am I going to unpack this, right? So my optimization problem is, given that I started at node U, I want to predict what neighbor V is in its neighborhood, right? And the question is, how do I model, parameterize this probability, right? This probability, basically what I'm trying to do is I'm trying to maximize the likelihood of random walk co-occurrences, right? I say, oh, nodes U and V co-occur in a random walk, right? Node V is a neighbor of node U. Node V gets visited from a random walk from node U. So the question is, how do I parameterize this probability? And here is how I will parameterize it, right? What I will do is the following thing. This function is called softmax, and I will explain why it's a good idea. But basically what do I do is I take the coordinates of node U and the coordinates of node V, and I do the dot product. And I exponentiate that, and then I divide or normalize by the sum of dot products of node U with any other node in the network, so that this is between 0 and 1. And the reason why this is called softmax is that basically what I want to ensure is that this will be greater than, in some sense, this will be greater than 1 if node V is the most similar to node U. Right? So in some sense, this summation down here will be approximately equal to the max over all the nodes. Right? So this will be close to 1 if node V is the most similar to node U. Okay? So that's why I want to do it this way. Right? Now it's clear how I want to set the coordinates such that all this giant sum is as large as possible. So here is everything denoted, right? So this is now sum over all the nodes U, sum over all the nodes V seen from random walks starting from node U, and then here is the predicted probability of U and V co-occurring in the random walk, right? Where, here is node U, here is node V, these are the coordinates of U, these are the coordinates of V, and this is a particular choice of how am I going to model this, probability of co-occurrence. One could go and choose other ways to model this. We chose the softmax for the reasons I mentioned. So what do we want to do now? Basically what this means is that optimizing the random walk embeddings basically means find the embeddings Z sub U that maximize this function L. Okay? What are some problems with this formulation, and what do we have to resolve? So one problem that this equation is not tractable is that it has quadratic complexity. The reason it has a quadratic complexity because I have a nested summation, two nested summations that go over all the nodes, right? I have the outer sum that goes over all the nodes, and then for every of those nodes, I have an inner summation, this normalization factor that again goes over all the nodes, right? So this means that in order to evaluate this function L, I need to go over all pairs of nodes. So the complexity of this is quadratic in the size of the network. And this is prohibitively expensive to run this on any kind of real network sizes. Okay? So what we will do now is we will take this term that takes linear time to evaluate, and we will approximate it to allow us to evaluate it in constant time. Okay? So the idea is that this normalization term from the softmax is the problem, and we want to approximate it. And the way we will approximate it is using a technique called negative sampling. Okay? So what we will do is we have this softmax and log of it, and the way we will approximate it, right? If I take a log of the fraction, I get log minus the log, right? But rather than working with this exp, we will actually think of it the following way. We will replace the exponent with a sigmoid function. So now what I say, this is the dot product passed through the sigmoid, and then I have the log from before. And then rather than summing here over all the nodes, I will just sum over k nodes that I pick at random. Okay? So where does the approximation happen? Approximation happens here because I'm not summing over all the n nodes of the network. I'm only summing over k nodes, where I pick these nodes at random from the network. And these nodes are called negative samples. I know the TAs were asking me this. These nodes can be the same, can be a node, so node U or node V can be part of these negative samples. It doesn't really matter. But the point is that you can approximate the sum rather than summing over everything. You just sum over a fixed number of randomly selected nodes. And now this becomes much more scalable. Yes?
Why is it valid to replace both axes with the sigmoid? Can you explain that again?
Why do I want to do this replacement with sigmoid? What is nice about sigmoid is that sigmoid will take any real value and kind of squish it between 0 and 1, right? So basically what this means is that I can, rather than taking the exponent and worrying about a normalization, by basically passing the dot product through a sigmoid, I already get something that looks like a probability, something that's between 0 and 1, right? So here I'm trying to show you the value of the eggs, and this is the value of the sigmoid function, right? So it squishes everything nicely between 0 and 1, crossing at 0.5 at 0, right? So you can now think of this as a different way to measure similarity, right? And then I have the similarity between U and V minus the normalization factor that I approximated using this set of negative samples or random nodes rather than summing over all of them. Okay? So this is what the negative samples are. I'm showing the same thing here. What turns out to work empirically better is that when you sample these negative samples, you don't sample them uniformly at random, but you sample them with probability proportional to the degree of the node, so that the higher degree nodes get sampled more often. And then, right, so k is another hyperparameter I get to choose, which is the number of negative samples I want to sample. And there is a balance I have to find, right? Like, if I pick higher k, I will have more robust estimates because I'm approximating the normalization term better. But higher k corresponds to higher prior on negative events and is also computationally more expensive. So I have to kind of balance the two out by choosing the right value of k. Question?
Why is the summation outside the log?
Why is the summation outside the log? Good question. The way you can really think of this is that I wanna approximate this part, and the way I will go to approximate it is by sampling. Now, in general, of course, this is not equivalent because I cannot take the summation out. In this case, the reason why this is fine is because all these guys will be between 0 and 1. Okay? And it's kind of how to say? It's an approximation that works well in practice.
Why are we not scaling it?
Sorry?
Why are we not scaling it by n by k?
Why are you not scaling it here?
Yeah, by n by k.
You could scale it, but because it's the same for everyone, it doesn't matter. Right? Right, so you would be scaling everything, you would be multiplying everything by the same constant. So in your optimization, it won't really matter.
When we use sigmoid, do we lose that property of the softmax?
Yes, I mean, we are a bit, but what we are gaining is that now everything is nicely between 0 and 1, and it allows us to apply all these tricks.
But we don't get that max anymore, right?
We don't necessarily get that max. Okay, good. So let me now step back and tell you how this works. Okay, so the way this works is I sample fixed length random walks of the network, and for every node I will collect this set, this neighborhood, this set n sub r of node u, which is a multi-set of nodes visited on random walks starting from node u. And then my goal will be to optimize embeddings of nodes z sub u such that this equation is maximized. Now, how am I going to optimize these embeddings? Is to apply an optimization method that's kind of the simplest of them all, which is stochastic gradient descent, which is basically I can compute the gradient of this function with respect to z, and then given the example, given u and v, I can then say, how do I need to update the coordinates z such that the likelihood improves? And really, I'm just kind of doing this in these small mini batches and keep updating these equations, these coordinates. Of course, the problem is non-convex, so I will get stuck in some local minima, but in general, these methods, because the number of parameters is large enough, they tend to converge to a good part of the space. So we will converge to some local solution, but the robustness of these local solutions empirically turns out to be quite good. Okay, so this is what I wanted to talk about in general about doing the random walk and then optimizing our objective function to find the coordinates. Now, what I talked so far more generally is that we talked about how to optimize embeddings given the random walk statistics. Now, the question becomes, what strategy should I use to generate these random walks, right? One idea is just run a fixed length, unbiased random walk starting from each node. And this is kind of what I presented so far. The issue here is that you want to have different notions of node similarity encoded, as Camilo was saying, right? So these fixed length, unbiased random walks are not necessarily the best solution. So the question is, can we make these random walks more interesting to capture kind of richer notions of node similarity? Okay, so now I'm answering your question. It was 24 and it's 33, so it's 10 slides. You didn't have to wait 17, okay? Great, so here's the idea, right? So this is now a second method we'll call node-to-vec. So the idea here is that, again, I want to embed nodes to encode similarity, but our goal will be that is similar as before, right? We want to frame this as a prediction task where we want to say what nodes are co-visited in the random walk or what nodes are neighbors of each other. And the key observation is that we need a flexible notion of node neighborhood so that we can capture different types of node similarity. And the way we can capture different notions of node similarity is through a biased, what we will call second order random walk that will then generate these network neighborhoods for us. Okay, so how are we going to generate this second order random walk? And the intuition comes from this idea that if you say, if I want to explore the network and I'm given case steps to explore it, there are kind of two extreme ways to do exploration. One way to do exploration is through the breadth first search type thing, right? Where I say, I will start here and I will just try to stay as close to the starting point and visit as, you know, the k nodes. So from node u, I could go to S1, S2, S3. Or I could use a very different exploration strategy, depth first search, where I would say, I want to get away from node u as fast as possible, as far as possible, right? So I would say, if I have 3 steps to take, I would take this type of exploration, right? And kind of what's the trade-off? The trade-off is, if I'm using this type of breadth first search exploration, I get a really good sense of how the network looks very locally, right? And if I do the breadth first search type of exploration, I get a better sense how the network looks kind of at the longer distance scales, right? So the idea is, right, that these two different exploration strategies will reveal very different kind of statistics about the network, right? So in our case, we will be generating these random walks of a fixed length, let's say 3, and you know using the breadth first search exploration strategy would generate a neighborhood set of S1, S2, S3, and you know using a depth first search exploration strategy in this case would generate neighborhood set of let's say 4, 5, and 6, right? And this would give you, the breadth first search will give us very local view of the network, and the depth first search gives a very global view of the network, okay? So now the question is, how do we kind of interpolate between these two extreme exploration strategies, right? We want to have a soft way to interpolate between these two extremes. So the way we can interpolate is to define this second order random walk that will have two parameters, P and Q. And parameter P will be what we will call the return parameter, where we will return back to the previous node where we came from. And we will have this second parameter that will be what we'll call in-out parameter that will tell us, would we like to move kind of away from the node U, or do we want to kind of stay close to node U, okay? That's the idea. So now let me tell you, we have this P and Q, let me tell you how we parameterize the random walk. Okay, so we want to have a random walk that explores the network, and the reason why we'll call it second order, because the random walk will remember where it came from, right? So far when we talked about, for example, PageRank is a first order random walk because you come to the node and you forgot where you came from. Here, our walk will have one step of memory, so it will know where it came from, and that's why it's called second order, okay? So imagine the following. The observation is the following. If you have a node, you start your random walk at node U, and you walk, and then you end up at some node W. Then from node W, there are only, in some sense, 3 directions in which you can go. From W, you can go to some other node, let's call it S2, that is at the same distance from U as W was. So when you are at W, you can stay at the same distance, you can go a step farther from you, or you can go a step closer from you, right? In a single step, there's nothing else you can do, right? If I think about distance from you, I can, you know, make a step backward and I go backward. I can make a step forward and I get closer, or I can kind of go sidestep and we maintain the distance. That's all. In the graph is the same, right? So, right, the idea here is that I know where I came from, so I can go back, okay? So here is what we will do. We will put weights on the edges based on where we came from. And these weights will model, do we stay at the same distance from you, do we go further away from you, or do we get closer back to you, okay? So how would we set the weights? If we are currently at W, this is how the weights would be set, right? We will put a weight of 1 towards the nodes that are at the same distance from you as we are currently. We will put weight 1 over Q on the nodes that are 1 step farther from U than we currently are. And we will put a weight of 1 over P on the edges that point to nodes that are closer to node U than what we currently are. Okay? So this is the idea, right? And these P and Q are, again, model hyperparameters, where P is the return parameter, basically saying, let's make a step closer to where we started. And Q is the walk away parameter. It's like, we want to escape the orbit of U, let's move farther out, right? And now, by playing with these parameters, I can force the walk to stay close to where it started, or I can force the walk to go as far away as possible from where it started, right? If I make Q to be small, the walk will want to escape. If I make P small, then this will have a high weight. The walk will want to go back, Okay? That's essentially the idea. This is what I just said, right? If I want breadth first search like exploration, I want this weight to be high so that the walker is likely to go back. I want to set low value of P. If I want the depth first search, if I want to go away from the starting point, I want to have Q to be small. So I want this edge to have high weight so that the walker goes that way, right? So basically the idea is, right, if I say I'm at W, I have a set of nodes, I parameterize these are now unnormalized transition probabilities where each edge has one of the three values depending whether that node is at the same distance from you as we currently are, it is one step farther away or one step closer. Okay, so here I try to explain that, and now I can run a random walk for a fixed number of steps and see what nodes it visits. Okay? Yes?
The random walk only has one step of memory, right? It doesn't actually remember where it originally started from?
The random walk has, yes, has one step of memory. It knows where it came from.
Okay, so in this case, W would only know that it came from S1, not really from you.
Sorry?
Like in this case, since that W would know that it came from S1, but not actually that it came from you.
But it knows where it came from and it knows what distance this node was at. Right? So if I know where I came from, then I know, if I know I came from here, then I know what does it mean to be at the same distance. I know what is to make a step farther out and what is it make to take a step closer. Right? So if I know what distance I'm away and I know what distance my neighbors are away, I can compute the weights of the edges. I can uniquely determine who is closer, who's farther, and who's at the same distance. Okay? So that's what I need to know. Yes?
If the graph is not a tree, how do you know, like, don't you have to run a shortest path algorithm on the entire graph first?
Yes, what you have to do is you have to estimate the pairwise distances to know this. Exactly. So you need to compute the pairwise distances.
Are P and Q the same at all nodes, or do they differ?
P and Q are the same across all the nodes, right? Again, you could make this more complicated. Right now, the idea is that these are two hyperparameters that you set, and they will be equal across all the nodes of the graph. Actually, it's a good question if, I know, changing this would buy you anything. I don't know, right? Maybe a good project idea, okay? So, but the point kind of is the following, right? If I do breadth first search, right? So if I have a low value of P, this means basically my walk will make a step forward and a step back, and a step forward and a step back, right? So I'll be kind of exploring the network very close together. And if I set the low value of Q, right, then I will walk farther and farther away from where I started. It will be always more likely for me to make a step farther than to stay at the same distance or turn back. So I will get a more macroscopic view of the network. And to give you an example, this is a social network of characters in the novel, where what was done here is we set different values of P and Q, we learned the embedding, and then we colored the nodes that are close together in the embedding with the same color, right? And here, for example, we have high value of P and low value of Q. So it means we are doing more depth first search type of exploration. So we go farther out in the network. And you notice how in some sense, the nodes that are close in the embedding, they correspond to these types of almost like communities in the network, right? For this set of parameters. But if we change the parameters and make high value of Q, which means the return parameter is high, then what we do in that case is that nodes that are close in the embedding, again, are colored with the same color, and you see that this more corresponds to the structural roles. You see that, for example, all these blue nodes are somehow connectors between the red nodes. We have these yellow nodes that are just like low degree peripheral nodes and so on, right? So we get different types of embeddings depending on how do we set these network exploration patterns, okay? Or how do we initialize the exploration of the network using the random walk. One thing, the last thing I want to show you, this is one example how this works, is also that these things work really well when network data is incomplete. So here are two experiments where this is basically saying, let's start with the network, but let's start removing edges at random. And here we say, let's start with the network, but let's start adding edges at random. Right, so here the network is getting sparser and sparser. Here the network is getting denser and denser, but we are just kind of throwing random stuff at it. And we are asking, how good of an embedding do we get? So this is some node classification task. Higher numbers are better. And you see that you can remove, for example, 50% of the edges in the network, and your predictive performance only slightly drops. Or here, you can add half of the edges at random, so you're just throwing random edges in, but again, your predictive performance doesn't deteriorate drastically, which is very good news that shows the robustness of these methods. What I also want to say is that there is very rich literature and very active research area around here, thinking about how do we do different kinds of biased random walks, how can we come up with different optimization schemes and optimize parameters in different ways. And also kind of what kind of network pre-processing techniques do we want to apply so that the notion of network similarity is most appropriate for our application, okay? So there is a lot of kind of different techniques that specialize further from what I said. What I want to quickly cover, or yes, I take your question.
Can you also bias the random walks by edge weight?
Oh, yes, of course. Everything I talked, so the question is, can you bias by edge weight? Yes, of course. So if you have a weighted graph, everything I talked to automatically applies where you say the transition probability is proportional to the edge weight. So you can easily do the deep walk, so the unbiased random walk on the weighted graph, or you could even try to say, what if I have edge weights, but then I have these P's and Q's that further modify the edge weights. So you can definitely do that. That's a great, yes, of course. Super question, thank you. You're thinking, that's great. Good, any other question? All right. Good. So let me tell you then how can you use these embeddings, right? After you computed the embedding, you can use the coordinates the following way. You can simply run a clustering technique and ask, what nodes are similar to one another to discover either structural roles or do community detection. If you want to do node classification, then you can simply take this inferred vector Z for a given node I and pass it through your favorite classifier, like a support vector machine, a decision tree, a linear regression, whatever you'd like to do. And then, if you want to do link prediction, now you have to reason about pairs of nodes, right? I have a pair of nodes ij, which means I have a pair of coordinates one for node I and another vector of coordinates for nodes j. And I can do different things. For example, I can concatenate the two coordinates, the two vectors together and think of this as a feature vector for edge prediction. I can do element-wise product. This is called Hadamard way of combining different vectors. I could also do a simple sum or the average of the two vectors and use that as an input to the classifier, or I could even do something where I'm asking what is the L2 distance between the two vectors and use that as a way to predict whether I think there will be a link or not. Okay, so there are different strategies. How can I take a pair of nodes and out of this pair of nodes take their corresponding feature vectors and create a new feature vector, either by some kind of aggregation, distance metric, summation, element-wise product, or just simple concatenation, and then I put this into my favorite classifier in order to be able to do this. So let me quickly summarize. So far we built on this basic idea that I want to embed nodes such that the distances in the embedding space reflect the similarities in the original network. And then we talked about that I can use different notions of node similarity, and we particularly, we had a dive into this notion of I want to use random walks approaches that define the node similarity. Now, the question becomes, what method should I use for my given task? There has been a lot of work done trying to compare different methods, and what the kind of conclusion is that no method wins in all the cases. For example, node2vec tends to perform really well on node classification, but less well on link prediction tasks. Random walk approaches are generally computationally more efficient than any kind of competing approaches. But in general, when you do this type of embeddings, you must choose the definition of node similarity that matches your application, right? So depending on how you construct the network and how you want to measure similarity, the best thing is to use that notion to directly optimize your embeddings. With this, I can finish here and take a few questions if people have any. Yes?
What is the benefit of learning the embedding independent of the task? Like, if you could find some way for the task to like affect the random walk in some way, like, wouldn't that give you embeddings that are better for the task at hand, and then you wouldn't have to have a downstream SVM or something?
It's a good question, right? So the question is, why would you want to do things in a task-independent way? The reason why there are several reasons why you want to do this. Sometimes you don't know what the task is. Sometimes you don't really care so much about the task as you care about kind of capturing the structural information of the network, right? And the same way, like for example, if you think about, right, when we embed a network, we embed the nodes. If you take text and you embed the text, you embed the words. And you don't care about embedding the words so that you can do really well on one particular task, but you care about embedding the words so that you kind of capture the semantics of the language. And here, kind of the goal is to embed things such that we capture the semantics of the network, right? And of course, there are methods where I can say, I really care about this task, so let's compute embeddings that are optimal for me to solve this task, right? Here, it was a more general idea of, I can use random walks to define this topological notion of similarity and learn the embeddings that way. Okay, you had a question.
I guess just like, what is a good way to take this kind of like node embedding and work with that for like bipartite graphs where your nodes are like heterogeneous? So say, yeah.
So what's the question?
So like, how can we take this knowledge of like node embeddings and work with like bipartite graphs where your nodes are of different types?
Great. So what would you do if you have bipartite graphs with different types? All these methods would still very nicely apply. What you can do is, if you have different types of nodes, you can further tweak the random walk, how it explores the network, for example. So everything we talked about nicely, like vanilla, already applies to bipartite graphs. If now you have heterogeneous nodes, different types of edges, you can of course go and specialize your random walk much more based on your application. And you can find the embeddings still. Yes?
Like love vectors for words, do we have like pre-computed embeddings or like access to pre-computed embeddings for, I guess, like important graphs that are often used?
Great question. So do we have pre-computed embeddings for graphs that are often used? There are embeddings that are published, but I think the difference from the language, right? There is, the 200 words of English that we all use. There is not 200 nodes that appear in every single graph. So as there is this kind of parallel with the language, it only goes that far. But good question. All right, let me, in the last few minutes, let me talk about now we talked about how do you embed nodes, but how do we embed entire graphs, right? So the idea is the following. What I'd like to do is, I'd like to take an entire graph and put it somewhere in the embedding space. And the reason why I would want to do this is because sometimes I want to reason about multiple graphs at once, right? So maybe I have graphs representing molecules, and I want to predict, is this molecule toxic or not? Or imagine I'm given some kind of transaction graphs, and I want to say, is this fraud or not? Right? So in many cases, I can have access to many small graphs. right? And I want to classify them in different ways. So how can I think of this is that I want to take the entire graph and map it into some high dimensional or low dimensional space where the entire graph maps to a single point. So the question is, how can we do that? And I'll give you, I think, 3 approaches how people can do that. Here is the simplest idea that people have proposed, right? So the simplest idea is run our standard graph embedding technique to embed all the nodes of the graph, right? And then to now create the embedding of the subgraph, what do? You simply sum up the embeddings of the nodes appearing in that graph or in that subgraph, okay? This is very similar to what they do in language, where they come up with the embeddings of individual words, and now if they want to have an embedding of the document, they just sum up the words that are in the document. So here we are doing something similar. We say, let's embed the entire graph, and now the embedding of the subgraph or the entire graph itself is simply the sum over the embeddings of the individual nodes. This was, for example, used in 2016 to classify different molecules based on their graph structure, right? Where the idea is, again, compute embeddings of individual nodes and then sum up those embeddings to come up with the embedding of the graph. That's idea number 1. This is simple idea number 1. Simple idea number 2 that's a bit more complex is this idea that we want to create a virtual node that connects to the nodes of the subgraph or the entire graph we want to embed. And then the idea is that the embedding of the subgraph is simply the embedding of the supernode that connects to all the nodes of the subgraph, right? So in order to embed the subgraph, we create this red supernode that links to all 3 nodes of the subgraph. Again, run our favorite node embedding technique. Whatever is the embedding for this node, that's the embedding for the subgraph. Okay? This is another interesting technique. And then the last thing I want to cover is actually a paper that was published this June, and it's kind of cool. So I wanted to give you some intuition. There is many more details. Here's the paper. Okay? So, and this paper introduced this notion of anonymous walks. And I thought this idea of anonymous walks is kind of cool. Okay? So we talked about random walks, and the way we represented the states of the random walks were simply the node IDs of the nodes that the random walk visited. So now, these guys proposed a different version of a walk or of a random walk that they call anonymous walk. And the idea of anonymous walk is that the states of the walk correspond to the time indices when the node was first visited by the walk, okay? So let me give you an example and then things should be clear. Imagine the walk goes from A to B to C to B back to C, okay? Then the anonymous walk for this random walk would be, we would represent this as 1, 2, 3, 2, 3. The reason is that node number 1 is visited at position 1. Node B is visited at position 2. Node C is visited at position 3. So now I'm going to node B. Node B was visited at position 2, so I put a 2 here. I go to C. C was already visited. It was visited first time at position 3, so I put a 3 here. Okay? And then, for example, a different random walk that goes from C to D to B to D to B would have the same anonymous walk, right? Because we start at C. C is the first node we visit. D is the second node we visit. B is the third node we visit. We go to D again. D was visited at step 2, so we put a 2 here. And then we go to B. B was visited at step 3, so we put a 3 here. Okay? And the reason why this is called anonymous walk is because kind of we forget the IDs of the nodes, but we remember when in the past have we visited that node. Okay? And here's another example from A to B to A to B to D. This will be 1, 2, and then 1 again because I'm at A, and then 2 again because I'm at B, and then 3 because I visited node D. Okay? So That's the idea. So what this means is that this number of anonymous walks increases exponentially with the walk length. And here is the graph I took from the ICML paper. This is the length of the anonymous walk versus the number of different anonymous walks. Okay? So just to show you, for example, the number of anonymous walks of length 3 equals 5. So here's a little exercise. What are the 5 anonymous walks of length 3? So one is 111, right? I started the node and I visit it 3 times, right? That's one possible one. So then the next one is 112, right? So this would be AAB or BBC or something like that, right? Where I first visit the same node twice, and then the third step I visit a new node. Then I can do 1-to-1, which is I'm a starting node, then I go to a new node, and then I go back to the starting node. Okay? Then 1-to-2, it's clear what it means. I start at a node, I go to a new node, and then I stay at that node. So it's a self loop or something. And then 1-to-3 means I visit three different nodes during the 3 steps of my walk. Okay? So what this means now, what authors propose is, how do you compute the feature representation of the graph? One option is to say, let me go and enumerate all possible walks in the graph of a given length L, right? So here L is my hyperparameter, and I will say I will enumerate all possible walks of length L in my graph, and I will simply count how often each one of them occurs. And then I will create a empirical probability distribution to say what fraction of times does each possible walk occur, right? So for example, if I set L equals to 3, I could take my graph, enumerate all possible walks of my graph, I would anonymize them, and then I would ask how often does each of these 5 different anonymous walks occurs, and I would capture this with a 5-dimensional vector, and I would think of that 5-dimensional vector as an embedding of my graph, where the ith coordinate of that vector would tell me what is the probability of having this anonymous walk a sub I in my graph. Okay? So that's first idea how you can represent the graph. The challenge here is that, I'm saying enumerate all possible anonymous walks on the graph and count them. And that is very, very hard. So the second way how you can make this better, this is now approach 3 idea 2, is you want to go and basically rather than do the complete counting, you want to do sampling, right? And the way you would do sampling, the idea is the following. Let's generate an independent set of m random walk and then anonymize them and calculate the empirical distribution of the anonymous walks. Okay, so is it clear? So I have, basically I say I want to generate 100,000 random walks. I pick a starting node at random. I generate a random walk of length L. I anonymize it, and I increase a counter in my vector. And I keep doing that 100,000 times, and then I get a vector of discounts, and then I normalize it to sum to 1, so I get a probability distribution, and this vector I created, that's my representation for the graph. What is beautiful? What is beautiful is that actually you can compute how many walks do you need to estimate your distribution over anonymous walks to a certain degree. And you get this kind of classical epsilon delta argument where you say, I want my distribution that I estimate through this sampling to have error of no more than epsilon with probability less than delta. How many walks do I need? Here is again the formula that tells you how many walks do you need to sample to estimate the distribution accurately. Now, eta is the number of possible walks of a different length L. This is my green, the bar chart with green bars that I showed before, right? To give you an example, there are 877 anonymous walks of length 7, right? So if I say I want walks of length 7, then there is almost 900 of them. And if I want to set my epsilon to be 0.1 and my delta to be 0.01, then I would need to generate around 122,000 different random walks in order to estimate this probability distribution over anonymous walks of the graph. And that would be one way to do it. And then the last way how you can use this notion of anonymous walks to learn the embedding for the graph is the idea is that we want to learn an embedding Z for every anonymous walk A, and then use those embeddings basically to aggregate them, either sum them up or average them in order to come up with an embedding for the entire graph. So then the question is, how would I embed the walk? Okay? And the way you would embed the walk is the following, is that what we want to do is we want to embed walks in such a way, here these walks are denoted by W, that I can say that I can predict what kind of anonymous walks occur in a neighborhood of a given node, right? So I say at node U, I have seen these different anonymous walks, and now I want to predict the probability, I want to predict what is the next anonymous walk I'm going to see, okay? So, and the same way as we are doing this in terms of node embeddings, we can do this now for walk embeddings, right? So now Z is an embedding of the anonymous walk where there is only a finite number of anonymous walks, and I will simulate these anonymous walks starting at some, arbitrary node U, and I will simulate capital T of them. So here is how this would work. I would say, let me simulate capital T different random walks starting at node U, each random walks of length L, okay? And now I will say, in some sense I have this set N as before. Before our set N was a set of neighbors, but now a set N is a set of random walks, right? So each of these is a L-dimensional vector or a set of node IDs. And then with each random walk, there is an associated anonymous walk, okay? And multiple different random walks map to the same anonymous walk. So now my goal is to to learn the embeddings of anonymous walks such that I can predict which walks can co-occur, okay? So here is what I want to maximize. I have I go a summation over, basically I have one more parameter, capital delta, that gives me my context window size. And then what I'm doing is I say, let's go over, let's have this sliding window of size delta over the capital T random walks I created, and then I say, I want to predict the next random walk given the walks I have seen in the past, right? So this is my context window size, capital delta, and given the previous ones, I want to predict the next one. How do I write out the prediction problem? I say the following. The probability of a given random walk that I see at time t, given the previous random walks, previous delta random walks that I've seen, will be simply e raised to this y of the walk that I've seen, divided by the normalizing constant over all possible anonymous walks that I have that I can see in my graph. And then how does this y function look like? How the y function looks like? It basically says, let me take the context of the walks I've seen, let me anonymize them and take their embeddings, take the average, learn this transformation matrix to come up now with, in some sense, with the embedding for the walk that I expect to happen next. Okay? And this way, I can again figure out using stochastic gradient descent what are these coordinates z of walks. What is now interesting is that these z's, there is one z per anonymous walk. And based on that, I'm basically predicting what is the next anonymous walk I expect to see at a given node, right? So something similar that what we did before, that we are generating random walks, anonymizing them. The difference is now that the set n is a set of random walks, not a set of nodes. And then again, very similar idea to before, where I say, given the previous random walk, predict what the next random walk is going to be. I can figure out how to learn the embedding of the corresponding anonymous walks that predicts random walks that tend to co-occur. So let me just summarize. There are generally 3 ideas that I covered. How can you embed entire graphs? You can embed the nodes and then simply sum their coordinates to come up with the embedding of the graph. You can create a supernode that spans the graph and then embed that supernode. That's idea number 2. And then idea number 3 was this idea of anonymous walks. And what is nice about the anonymous walks is that they take this super large space of random walks and kind of compress it down to the space of anonymous random walks. And this gives you kind of nice dimensionality reduction that you can even think of describing the graph by describing it with the frequencies of different types of anonymous walks that occur in this graph. So you could either go and represent the graph with the distribution over the anonymous walks, computationally intractable. Idea 2 is sample the walks, anonymize them, and then measure the distribution over these sample random walks. And then idea number 3 is embed anonymous walks. And then when you say, how do I embed the graph, is to say, let me aggregate the embeddings of the anonymous walks, and this gives me the embedding for the graph. So this is what I wanted to cover today. I know we covered a lot, basically both from the embedding of nodes as well as for embedding of entire graphs. The slides include pointers to papers that we covered, so there is much more detail in the papers. And then one thing we didn't cover is what optimization techniques do you use to actually learn these coordinates. And as I kind of hinted, optimization techniques are very simple, but work really well in practice, and they are all based on stochastic gradient descent. And we will learn about stochastic gradient descent kind of further down in the class. But I wanted to cover this a bit earlier because a lot of projects are on these types of topics, and many of you are excited. So I wanted to give you some way to think about these problems. Thank you very much, and I'll see you on Thursday.